everybody. Welcome back to the dev track. Next up, we've got Rudy. Rudy is talking about cloud native CloudStack deployment. So everybody, please give Rudy a nice, warm, virtual round of applause. Over to you, Rudy.
Thank you, Giles. Thank you very much. So today, we're basically going to talk about a little research experiment that we at Indicus have been trying for a while, which is all about running CloudStack as a cloud native Kubernetes deployment. And it's been a very interesting journey so far. And unfortunately, while we really wanted to be ready for the conference to be able to present a working installation, we weren't able to get there. And I think it's a great opportunity to try and address what this particular experiment looks like, why it's such a great idea, and where did we go wrong, and what are the things that we need to do in order to get CloudStack to a point where it becomes, say, a Kubernetes appliance of sorts. So just a quick introduction about me. I'm essentially an infrastructure and data engineer. At Indicus, I currently head our DevOps and our R&D teams. I also happen to be an amateur historian, so we can also talk history someday if you want. And do hit me up if you want to shoot the breeze on the state of infrastructure. And a quick introduction about what we do at Indicus. We specialize in monetizing edge clouds. We help service providers across 7 countries, across 4 continents, quickly get started with becoming edge cloud service providers themselves using Apache CloudStack as the base. So the problem that we were trying to address a few months ago, so CloudStack 4.15 was out, and we realized that this is great. It's time to start testing it because we obviously want to start pushing it out to our customers as well. But then we kind of hit this roadblock where we want to test multiple versions across multiple environments. Maybe there's a separate storage layer, maybe there's a separate networking layer. Maybe one deployment is on bare metal and one is on para-virtualized hardware. And we realized that when we want to go in there and start setting these up, it's a really painful process. For one, obviously, there are multiple setups, multiple infrastructure setups, so that's a problem. Each needs its own management server. The installation process is also rather manual as of now. And we feel that infrastructure as code only helps you so much. I mean, yes, you can go in there and write Ansible playbooks, but after a while, management becomes a huge pain. What do you do when a management node goes down? In production, it's obviously a huge nightmare. But even in dev and testing environments, seeing a management node goes down obviously takes away time from what you'd allocated to test that new installation. What if something happens to MySQL? Setting up a replicated MySQL cluster is not that easy anyway. These were the kind of pain points that we started seeing a lot. And we're like, how can we try and move around these? How can we get past these? So, one of us had this bright idea, why don't we start looking at running CloudStack as a Kubernetes appliance? The main feature here is that the management server and the usage server, they start running as applications managed by Kubernetes. And then we wanted to go a step further. Well, we wanted to go multiple steps further. We wanted to make the idea of adding hosts, especially KVM-based compute hosts, as easy as adding a node to a Kubernetes cluster. As of now, the process is, you install KVM on a host, you install the CloudStack agent, and then you tweak the networking, and then you add it to CloudStack. We wanted to try and automate that, where you just add a node to this management Kubernetes cluster, and voila, you have a compute node ready to be run. Kubernetes takes care of everything. That means you can suddenly start deploying multiple CloudStack versions on the same infrastructure because it's Kubernetes. So you can have multiple deployments running off multiple branches from the same code base. Eventually, what we wanted to do was we wanted to spend less time installing stuff, and we wanted more time testing and putting CloudStack through its paces. So let me just quickly walk you through the architecture. It's a very bare bones diagram, mind you, but I think it'll serve our purposes here quite nicely. We've been doing a lot of our testing on vSphere because it allows us to quickly get set up with para-virtualized infrastructure really easily. So you've got a vSphere cluster. It doesn't matter how many nodes there are. I mean, that's really up to you. You can even just go ahead with 1 physical host. You can go ahead with 3. It doesn't matter as much. We've got an external load balancer sitting outside. This could be something as basic as HA proxy. And then you've got multiple virtual machines running on vSphere. You've got a cluster that consists of a master node. This is a Kubernetes master node. Now, this is only responsible for ensuring that the cluster stays up and, the applications that you schedule on it, like CloudStack's management server, also stay up, or like MySQL, which is what the management server needs to store its internal state, that stays up. Then you have a specially designated Kubernetes worker node, which we call the controller node. This node is only responsible for running management components, so usage, the management server itself, MySQL, and so on and so forth. And then you can add as many compute nodes as you like, which are also Kubernetes worker nodes, but they're just annotated in a certain way. They're probably annotated with something, say, compute. And that helps Kubernetes differentiate between a node that's running the management server and a node that's supposed to run, test virtual machines. So the flow we came up with to kind of make this happen. We came up with Terraform. We wanted to use Terraform to start spinning up the underlying infrastructure. So a bunch of Terraform plans that talk to vSphere and spin up, virtual machines that make all this happen. Then an Ansible playbook that takes those virtual machines and orchestrates a K3s cluster on it. Why K3s? So, lots of Kubernetes distributions out there. I mean, at this point, you throw a stone and you'll probably hit a Kubernetes distribution. We went with K3s because installing K3s and managing it is super simple. As opposed to more specialized or bloated Kubernetes distributions, K3s does not ship with a lot of components that you don't actually need when you're running it on on-prem hardware. Usually those components are needed when you run it on, say, a public cloud. Then, a specialized Helm chart for spinning up MySQL, which is distributed, replicated. And then a bunch of Kubernetes manifests that try and spin up a working CloudStack management server. So now I'll quickly just give you guys a demo of what this looks like. So I've got Rancher running here. So again, we're big time Rancher fans and we use it for just about everything. So we've got a cluster running here that we call LeanStack. Now this cluster is basically what's supposed to run everything, MySQL as well as the CloudStack management server. So we'll just quickly get started with using a community Helm chart for launching MySQL. Now, while this is the process that we use, nothing stops you from using, a Helm chart of your own for MySQL. Nothing stops you from using, say, Bitnami's. Nothing stops you from spinning up your own MySQL stateful sets. It's all up to you. As long as it's accessible throughout the cluster, it doesn't matter how you spin it up. We just use this system because it's just so easy. Great, so now we're just going to give this a couple of minutes while it spins up. And in the meantime, I'll just quickly give you a walkthrough of what the code for spinning up whatever this experiment is looks like. So as I mentioned, we have a bunch of Terraform plans, which essentially orchestrate two virtual machines, but this is configurable. So if you want like a bigger cluster for multiple CloudStack deployments, you can obviously go ahead and tweak that. And this plan essentially talks to vSphere and spins up two virtual machines with SSD storage backed drives attached to them, and with one management network interface, which again can be tweaked as long as you have more network interfaces, which you want to use for, say, your compute nodes. You can attach those too. And then the Ansible playbook that I mentioned, which simply just goes into the VMs that we set up using Terraform and spins up a very basic K3s cluster out of them with certain specific defaults. And it uses MySQL as its internal state database. And then finally, we have our manifest here, which we will go into in a bit. Let's see if MySQL's up. And it seems to be up. Great. So now let me quickly show you what the manifest for running the management server looks like. Now, the CloudStack management server presents some very interesting challenges, which is where our experiment started faltering and, as they say, running out of steam. The management server essentially assumes that your server is going to run on one particular machine, and that machine will also be responsible for setting up the database. And that's where things get really interesting. Now, that introduces a certain amount of statefulness, because when you set up your database, CloudStack creates a db.properties module, which is then eventually used by the management server to connect to the database. But this is Kubernetes we're talking about, right? Like stateful, you can do stateful, but then by default, your workloads are not stateful. So how do you try and get around that? How do you ensure that you're able to run your DB setup and pass along that MySQL, that db.properties module to the CloudStack manager? So this was a very interesting pattern that we then tried to implement, where we use something called init containers. Inside Kubernetes, you can use an init container to run jobs that are only supposed to be run once before your application boots up. So to give you an example, in fact, this is probably the best example. You want to set up a database, you want to run a schema migration script before your application boots up. So you get to run an init container. But the biggest disadvantage with this pattern is that if you then, let's say your application goes down and you need to reapply this manifest to the cluster so that you bring the application back, unfortunately, this script runs again. So that's the first roadblock that we hit. How do we stop the database migration, the database setup script from running again and again and wiping out whatever progress we had? For which we have a bunch of ideas that we hope to implement in the next few weeks. We just simply didn't manage to have enough time to look into this because there were just so many challenges coming in. This was one challenge. Another challenge is with the CloudStack manager. CloudStack uses systemd exclusively to manage all its applications. Now, the way systemd works is that it runs as the init process, and then it forks. Each systemd definition leads to a forked process. But containers by definition are single process, and they're supposed to be single process. While people do manage to run multiple processes inside them, it's usually not, it's not recommended. So how do we go in there and get CloudStack to run without systemd? And this became another very interesting challenge because the CloudStack management script exclusively focuses on systemd, which then leads to interesting patterns. You have one container image that I've built over here that contains all the management components that are needed to run CloudStack. The same image then needs to be deployed with multiple entry points. One entry point for just running a Java app, which is your management server. Another entry point for just running the usage server, and so on and so forth. And that's where things start faltering. And then finally, how do you ensure that whatever db.properties file the db setup script creates is then passed along into our container? This thankfully was easy enough. I mean, you can pass, Kubernetes allows you to pass persistent volumes between containers within a single manifest. What becomes interesting to note is that by default, before you start with this, you need to ensure that every properties module that CloudStack needs is stored locally as a config map, which can then be injected inside. Because if we just inject this, CloudStack fails. It cannot find the other configuration modules that it needs. So let's go ahead and try and run this and let's see what happens. Great. So now let's quickly take a look here at what's happening. Now, what Kubernetes has done is it's started spinning up two separate containers. One of them is the init container, which is what's supposed to run our DB management setup. Until that container doesn't exit successfully, the CloudStack one doesn't boot up. So let's see what's happening here. Yeah. So now if we look at this, now what essentially happens is when you install CloudStack through a package manager like apt or yum, everything is brought to your server, including all .properties files. We noticed that while our container image contained those files, trying to move them around as a volume would typically fail because CloudStack doesn't just need this file, it needs a lot of separate files, right? When we try and attach a separate volume so that we can run the DB setup script in one container and then pass off the proverbial baton to our main container, it fails because it's not able to find this file anymore, even though we've tried to mount it from the image. Now, the best way that we thought of getting around this was to create multiple config maps, except because of the number of configuration modules that CloudStack needs, that would lead to at least 10, maybe 12 config maps, which in itself is not the best of patterns, because in Kubernetes, at least, you should try and keep your manifests as simple as possible. So this was a very interesting challenge, one of the interesting challenges that we ran into. So let me just quickly switch back to my deck and talk about all the problems that we faced and how we could possibly get around them. So as I mentioned, converting ACS configuration files into Kubernetes config maps, that theoretically allows us to inject all of these files at runtime instead of depending on a container image or a package manager to provide them for us. Then one was, like I mentioned, how do we break out the database setup as a Kubernetes job or as an init container, where the idea is that once the job has succeeded, it's written all its values to whatever configuration files it needs to write values to. And those updated files are then made available to the container. This is where config maps kind of tend to fail, because whatever we do here does not get persisted back inside Kubernetes. It just stays inside that volume. If anything happens to that volume tomorrow, then technically we've lost our entire setup. We need to redo it. While redoing it barely takes a couple of minutes, it's bound to be a very irritating experience. Then, of course, we need to discard systemd, because if you're trying to run CloudStack as a Kubernetes application, systemd would just not cut it. Systemd was never meant for containers, and simultaneously, containers were never meant for systemd. They were meant to run single processes. So the best way forward here is to not run the management script, which runs, which adds jobs to systemd and starts them up and enables them to be available on a reboot. We need to see how we can take the Jetty server, the embedded Jetty server, and run the management server using that as a pure command. And that allows us to then break everything as separate deployments, because then the management container runs separately, the usage container runs separately. Excuse me. Then finally, we come to the compute hosts, which is something we weren't even able to touch, but which come with very interesting challenges of their own. CloudStack typically needs SSH access, right, to connect to a compute node. And it's over SSH that it then talks to the KVM hypervisor that's installed on that node. And it talks to the CloudStack agent and, orchestrates virtual machines and manages them for you. When you try and look at running a container or a pod on a compute node to serve as your compute agent, you start running into a very interesting problem, because the container's network is different. The host's network is different. How do you reconcile the two? Now, the easiest and the most obvious way is to run something called a privileged container. Privileged containers, which by the way are a very bad idea, allow you to run containers as a part of the underlying host's network, and they have access to everything on the host, the entire file system, the process space, system calls, everything, which is why they're such a bad idea to run. And they obviously introduce a massive security vulnerability into any setup where you push them into. We don't want that, do we? So then we started thinking about a very specialized Kubernetes operator. Kubernetes operators are basically small agents that can be installed inside a cluster. And they allow you to modify the state of the system and to have very customized actions whenever you do something on the cluster. So for instance, there's an operator that allows you to, attach a disk from underlying storage to a volume, to a node when you request for it on Kubernetes. That's what an operator does. It allows you to watch for changes to a cluster or to resources running inside a cluster, and then undertake any action that you'd like. So we were thinking, what if we write an operator that listens to a custom resource, which we could call, say, a CloudStack compute node. Every time a user creates a CloudStack compute node, they just tell the Kubernetes cluster, look, here's the IP address of the node, here's the SSH username, here's the SSH password. And they apply that to the cluster. The operator watches out for that, logs into that compute node, installs everything that needs to be installed. The KVM agent, the CloudStack agent, any networking, IP tables rules, anything. And then it tells the CloudStack management server that, hey, look, there's a new node here. Here are its SSH credentials. Why don't you add it to one of your zones? And that's it, it's done. So as a human being, as an operator, as a CloudStack manager, you don't have to do anything. You don't have to go into that compute node and actually run commands and so on and so forth. Kubernetes does everything for you. Rather, the Kubernetes operator does everything for you. So the where I see this going, first of all, I think maybe I should address the third point here. Will this be ready for production? And that's a question, we've been asked a lot. We don't think so. We don't think this will ever be ready for production usage. We think that if you want to run a CloudStack cluster for production, which dozens or maybe hundreds of people will use, this is a system you should probably not be using. But we were trying to build this to make life slightly easier with dev, with testing. If you're contributing to the CloudStack code base, for instance, if you're writing custom modules, or if you're just contributing to the core code, or if you're somebody who wants to create CloudStack based deployments for service providers, either way, your life is going to be a lot about testing newer versions or testing multiple versions of CloudStack that have different configurations or different storage layers and so on and so forth, or maybe different network topologies. In that scenario, yes, we believe that this entire exercise could be very useful, because instead of continuously spinning up new CloudStack deployments by manually undertaking that entire installation process, the idea is that you just do a couple of clicks, maybe type in a couple of commands, and everything's taken care of. And along with that, Kubernetes ensures that your deployments never go down. It ensures that your management servers never go down. It ensures that if your compute node goes down, you're notified, and any action that you might like to be undertaken is actually undertaken. And eventually, we would love to see this being used with the likes of Harvester. Harvester is this very powerful HCI, open source HCI platform that Rancher's been building, which runs completely off Kubernetes and KVM. And we liken Harvester a lot to the likes of Nutanix or VMware. vSphere is great, Nutanix is great, but they're not clouds, they're not orchestrators, they're hypervisors. And that is where we see Harvester going as well. So if we could harness the kind of power that Harvester comes with and allow CloudStack to be able to talk to it, I think that's a great open source solution for deploying quick edge deployments, where obviously the investment that you want to make is not a lot. And then finally, this all gives rise to what I've been talking about a lot, the whole concept of a CloudStack appliance, where it's just drag and drop. We may not be great fans of Windows, but I think their setup process is amazing. You just double click and it's done. And when 10 years ago, when the first idea of cloud appliances came in, I think that was a huge game changer. You just click on something and suddenly a MySQL database is installed, or you click on another thing and a Ruby on Rails environment is installed for you. Why not have something similar for CloudStack, but something that's more cloud native? That's the direction where we'd like to see this go in, with perhaps your help as well, if you'd be so inclined. So yeah, that's the GitHub link for whatever work that we've managed to do as of now. And I'm now all open for questions.
Brilliant. Thank you, Rudy. Very, very informative. A few questions come in. Let's dive straight in. Harry has said, because obviously you touched on Terraform. So do you have any plans to use the CloudStack Terraform provider? He's asking this because I see you already using Terraform with vSphere.
Right. So the CloudStack Terraform provider is essentially meant for orchestrating resources on top of a CloudStack deployment. For us, Terraform has a very different purpose, which is orchestrating the resources we need to be able to run a Kubernetes cluster that in turn runs CloudStack. So I think for us, the CloudStack provider for Terraform does not make a lot of sense. But I've been following it very closely back before it was, merged into the Apache Foundation, and I think it's amazing. And I've had some really good results with it.
Cool. So somebody who's anonymous has posted a question. I really like the idea of deploying CloudStack in a, see if I can pronounce this, Kubernetes way. I know that isn't the way you pronounce it, but it's not inherently Kubernetes compatible and causes issues such as DBS, multiple files, config maps, etc., with a lot of workarounds. So considering all of this, isn't this kind of anti-pattern? I think I know where the guy's going with this question, whoever asked it.
Well, yes. So to some extent, you could say it is a bit of an anti-pattern, because why are we taking something that, so let's be honest, CloudStack was architected and developed in a time where, forget Kubernetes, we didn't even really have containers. And when we did, nobody really knew anything about it. But at the same time, I think that CloudStack is still relevant in today's world. Which is why we're not looking at force fitting this in for production. We're looking at this exclusively as a system that tries to make the lives of people easier. Those people who are either developing on CloudStack and need to spin up quick environments and not deal with the grunge that's associated with installing everything themselves, or people like us, people who are using CloudStack to deploy edge clouds for service providers. And obviously, we need to stay ahead. We need to be able to tell our customers what to look out for and what not to look out for. We need to constantly test multiple versions. If there is a way in which, say, a massive effort can be undertaken right now to create not a forked version of CloudStack, but an appliance that allows us to run CloudStack as a Kubernetes appliance without it being apparent to the user, all the stuff that we've done, I think it's totally worth it.
Yeah, I get it. And actually, I'll just sort of extend that question a bit. Rohit earlier was talking about MBX, and we've had Dev Cloud, and there's Trillion, all these other things which are aimed at people who are testing and working on CloudStack. Just compare that with the sort of work you've done here as an alternative.
So, so the thing is, when it comes to MBX or when it comes to Trillion, I might be wrong here, but I personally feel that they're geared more towards CloudStack developers, people who spend their entire days contributing to CloudStack. This, on the other hand, to be very fair, is geared more towards people who spend their entire days deploying CloudStack for service providers or for private enterprises, and who then need to be able to say, okay, we've tested everything in this new version. These are the pain points that we feel are valid, and so on and so forth. So I think Trillion is geared more towards a CI/CD sort of approach for CloudStack, while this is definitely not geared towards CI/CD at all. It can be, but that wasn't one of the goals we had in mind.
Cool. Okay. And final question, Vlad is asked, isn't running CloudStack hosts in a Kubernetes going to slow everything down? Sorry, I'm paraphrasing that question.
Okay, not exactly. So I actually at first thought that's exactly what we thought too, but then we realized, let me just quickly go back here to the architecture diagram, if that might help. Right, here we are. So these are our compute nodes, if you can see my screen. Now, these nodes are not running anything but the compute agent as well as user virtual machines. They're not running any Kubernetes-based workloads. The only reason they exist inside the Kubernetes cluster is for us to make it easier to manage them, easier to add them, easier to remove them, and easier to be notified if one of them goes down. But the performance, I don't think there is a performance hit per se, because they're not running anything but what they're supposed to run, which is user virtual machines, like for KVM.
Get it. Brilliant. Well, thank you, Rudy. That's just about all of the questions. Everybody, please give Rudy a virtual round of applause and say thanks. I really enjoyed that chat. For those of you staying on the dev track, next in 10 minutes, we've got a talk from Guido about Ceph and CloudStack. Over on the other track, we've got to talk about monetization around CloudStack. So see you there.